The project title for today is Implementation of Snake Game on FPGA board using VHDL.
This is Arav.
And this is Sarvesh. This project presents the hardware implementation of the classic Snake game with extra features using VHDL on a ZYNQ7000 ZED board. The design incorporates input through the buttons of the ZED board for directional control and VGA output for display rendering.
All components were synthesized, implemented, and successfully tested, with the complete system providing an interactive gaming experience that follows the rules of the classic Snake game. As we can see, this is a multiplayer game supporting player 1 and player 2. To start the game with the player 1, we will be pressing the right or the left button on the FPGA console. As you can see, by playing the left or the right button, we have started the game. The current objects in the game are the snake, the poison mines, the fruit, and the walls. On eating the fruit, as you can see in the game denoted by the blue dot, the length of the snake is increasing by 1 and the score on the top right is increasing by 2.
Now we can see that after eating the apples, the length of the snake is increased by a good amount. Now I'll show how the mines work. Now mines are denoted by red color on the display screen. If I eat a mine, the length of the snake decreases by the 1, and correspondingly you can see on the top right corner the score decreases by 1. Now we can see the score after eating an apple is increased to 18 on the top right corner, and correspondingly it is also increased on the ZED board LEDs. The score array is 7-bit array, so we can see corresponding binary digits and convert it to decimal to see the score.
To get eliminated in this game, a player has 3 choices.
The first one is self collision, when the head of the snake collides with its own body.
As you can see, the game has ended.
The second way of death is collision with wall. As we can see, the head of the snake collided with the boundary of our display screen, so the player got eliminated. Now the third way to get eliminated is if we eat mines continuously and the length of the snake goes back to 3, then our snake gets eliminated. As we can see, we had increased our length by 2, and again we ate 2 mines and length decreased to 3 again, which is the original length, so the player got eliminated. As we know, this is a 2-player game when player 1 gets eliminated. As we can see, player 1 score is represented by 5 over here. Now for the player 2 to start playing, either we have to press the top right button or the top bottom button. Now the player 2 chance starts. As we can see, player 2 is denoted by blue color. All the rules apply the same for player 2, and when player 2 gets eliminated, we can see the final score of player 1 and player 2.
In this project, Vivado serves as the central toolchain for developing and implementing the Snake game on the FPGA using Verilog. It plays a crucial role in the multiple stages of the hardware design process. As you can see, here is the code, the project code that we have implemented with all the various files that are being implemented in the project. Firstly, Vivado is used for RTL design, which is register transfer level design and simulation, allowing us to write, test, and verify the Verilog code that defines the logic of the game, including snake movement, collision detection, and score tracking. The RTL design generated by the Vivado software is here. As you can see, it's a marvelous design, which is at its basic level comprised of gates and mux logic. After verification, Vivado performs synthesis, which converts the high-level Verilog code into a gate-level netlist. This is followed by implementation, where Vivado maps, places, and routes the logic into the specific architecture of the target FPGA. Finally, Vivado generates a bitstream file, as you can see here, to ensure the design meets performance requirements, especially for real-time VGA output and game responsiveness. FPGA architecture is as an integral part of our whole design. The FPGA architecture consists of 3 major parts. First one is the configurable logic block. The configurable logic block consists of a mux that takes inputs from a lookup table and an integrated D flip-flop. The lookup table takes the input from the bit stream that we have generated from the Vivado software. Another important part of the FPGA is the switching block. A switching block is a matrix that consists of six switching architectures that coordinates all the CLBs around it. FPGA also consists of an input-output pad that interconnects the inputs and outputs of all the facilities that an FPGA provides us. As you can see, there is a plethora of input-output sources such as switches, buttons, output LEDs, etc. Input-output pads are responsible for coordinating all of these. The field programmable gate array is the code hardware platform used to implement and run the Snake game. Unlike a traditional microcontroller or a microprocessor, the FPGA allows us for custom digital logic to be configured using Verilog. This has enabled us precise control over the game logic operating on the hardware level. All components of the game, may it be snake movement, food generation, etc., are implemented directly as digital circuits on the FPGA as shown before. This allows for true parallel processing, low latency, and real-time response. The FPGA processes user inputs from buttons as shown or switches and updates the game state accordingly. It also generates synchronization signals that we have defined in our clock files and pixel data required to drive the VGA display. The reconfigurable nature of the FPGA makes it ideal for experimenting with hardware games designs, allowing changes to the game logic without modifying the physical board. In this project, FPGA acts as the brain of the system, executing the logic and coordinating all inputs and outputs.
Now we move on to the coding part of our project. So the code consists of two folders, snake movement and VGA. In the snake movement part, we read how the snake movement, apple generation, mine generation, and everything takes place. And in VGA folder, we learn how the clock, button inputs, constraint files, and how our interface and VGA display takes place. Now we first see the snake moment folder, in which the first module is apple generator. So as the name suggests, in this we generate apples at random position. As we can see one algorithm over here, which generates apple at random positions, and then over here we see if apple is eaten or not. Basic logic is if the head's x coordinate and y coordinate matches with apple's x coordinate and y coordinate. And then over here we just see the score. If apple is eaten, we increase the score by 1 and add cube 1. This is for increasing the length of the snake, and this is to increase the score of the snake. And then over here we see if apple is generated or not. And over here min x and min y are basically the boundary conditions of our display screen, so that apple does not get generated out of the boundary. Now we look at the mine generator module. As the name suggests, again it generates mines at random locations. So over here we are having 4 mines in total, which are being generated at random locations. Now mine active is like if the mine is active at that moment or not. Mine hit mine is basically if the snake touches the mine, and reduced length is that if the snake touches the mine, then the length of the snake should be reduced by 1. So yeah, this is the basic code in which we generate mines at random position if and if mine active is equal to 1. And then we see the collision condition over here, if the mine hit is 1 or not. If the head x and head y coordinates are equal to the mine x and mine y coordinates, and our mine active is 1, that is mine is present. And if collision happens, then we deactivate our mine active symbol. So now the snake moving logic. In this, we just see how our snake moves up, down, left, right, and how the blocks are being added and how the blocks are being reduced in our snake. So yeah, this is basic code for it. Over here, we manually put the location of our snake. So as I had earlier said, our snake is of length 3. So these are the coordinates of our snake, which are predetermined by me. So yeah, default value of the snake with length 3 and fixed position. Below we manually set the position of the snake and the length of the snake. And over here, what I have limited is my length of the snake can't go above 30. So 30 is the max length of my snake. That is one constraint I have in my project. The score will get updated even though the snake eats the fruit, but yeah, the length would increase. And this is pretty much hard coded. And over here we can just see, instead of using for loop, we just see hard coded. I did it hard codedly. And over here we see if the wall is detected or not. This is the code for wall detection. This is the code for self collision. If at any point the head of the snake gets touched with itself, yeah, any of the particular pixels, yeah, block. And yeah, this is pretty much hard coded code. Now if collision is there, we don't move the head of the snake and decrease the length. So our code works is if the length is increased by 1. So over here it appears that each segment is following the head like a chain motion. Each segment takes the position of the segment in front of it. So the 0th block will take the 1th block will take the place of 0th block, and 1 blocks it will move ahead. Yeah, this is the pretty important logic of our whole game. Here the movement of the snake is controlled by the direction of the snake. We change the direction of the snake here. If it's changed to left, we do direction next left, and change to right, direction next right. Yeah. And then here if the snake is dead, then we don't want to increase the length of the snake. Else if the apple is eaten, then the length of the snake is increased by 1. So we do over here. Yeah, now over here we do the boundary check conditions and we display mines on our particular screen. So the next module is stop greedy snake. As the module name suggests, in this we combine all the other 3 modules seen previously: the apple generator module, mine generator module, and snake moving module, along with some VGA controls, buttons module, which I'll explain afterwards. And the basic use of this module is to generate player 1 and player 2 and keep a track of player 1 score and player 2 score over here. Team selection and scoring logic. So we start with team 1, left right buttons to select team 1, and up key and down key press to select team 2. Yeah, when first team's game is ended, then we save their scores and show their scores, and same for team 2. Now we come to the next folder, which is VGA. So in this folder we can see the first module is button input. Over here we just take the input left key, right key, up key and down key, and accordingly we just set its values. The second clock is clock unit. In it we just generate clock, a normal clock. Clock.v, this is a very important module for our display rendering, as the frequency which we get from FPGA board is around 100 megahertz, and our VGA display module does not run at 100 megahertz. The max capacity for it is around 25 megahertz. So over here we just generate frequencies which are of less than 100 megahertz from 100 megahertz for 25 megahertz, 20 megahertz, so that we can smoothly run our game or render our game on VGA display board. The next is font ROM. In this we have basically how we display the snake game P1, P2 pixels on our interface display, which we had already covered. So this is basically the pixels where we are hard coding the values, as should be shown here: N, A, K, E, and G, M, P1 and P2. So the game status control module, as the name suggests, again we just see how our game is controlled and what's the status of our game. Restarting if it's in restart mode, start mode, playing mode, or if the player has got eliminated. Yeah, and we just see if the keys are pressed, then we say game status play, or else we say game status start. If any kind of elimination happens, that is hit wall, hit body, or hit minimum length, that is 3, then game status will say die. And over here if die is there, then we just have the clock included. Now this interface display. So this code we had searched it online on the official website of the ZDD board, ZYNQ7000. So in this we see how we basically display all the colors or the head, body of the snake, the mines and everything, how the pixels are situated and how do we display it. So yeah, this is pretty much which was given on the official website, which we have shown. Over here we can see how our snake game display on the interface is shown. Over here the bits and everything. Yeah, so this is pretty much which I had got online. Then is VGA control. This VGA control is just the combination of the clock unit and VGA display unit. And in VGA display unit we just display all the colors and everything what we have. The main important crux of it is HSync and VSync, which was again given on the official website of FPGA ZDD board. How do we do sync between the horizontal and the vertical part. So one more thing about VGA display we have to keep in mind is the VGA display consists of 640 into 480 blocks, and each block consists of 16 pixels. So nearly we have 40 rows and 30 columns. So to coordinate between these columns and everything, we have HSync and horizontal sync and vertical sync. And this is color out and XY position registers. And in VGA generator, yeah, it's pretty much similar to VGA control, in which we just integrate VGA display and clock unit. Now the last part of constraints file. So the main use of constraints file is to map the input of our code to the pins on the FPGA board. For example, you can see score 6, score 7, score 5. So we just map it to the particular LEDs, and these LED pins are basically given on the FPGA board. Same for color out 0, color out 1. This is red, blue color, this is green, and this is red, which was the pin number Y21, Y20, which is again given on FPGA board. And this is for reset, up, right, left, down button. So for this pin, we refer to the official documentation of ZDD board, Zinc, evaluation and development hardware users guide. In this, we can see all the particular pins and that all we have to use. So yeah, over here we can see the pin numbers, ZNQ pin, and what all pins does. This is the VGA port, which gets connected to our VGA display. And for this, we have for red video, these are the ZNQ pins, green video, blue video, and majorly the horizontal sync and vertical sync, which I explained was the most crucial part of our VGA interface.